All right, so welcome everybody to our second week of PHYS1210. So we have, we're going to move on to a slightly different topic today and this week in the lectures. Like I said last week, we also have the tutorials and the quizzes starting up this week. So the tutorial classes, there's a couple of them this afternoon, are going to be on what we covered. The problems are going to be based on what we covered in the lectures last week. And then there will be a quiz to do. You've got until, I think, the end of the weekend or maybe even next Monday to do that quiz. That quiz is going to be based, again, on the particle physics stuff, so on this week's tutorial, last week's lectures. You can do the quiz as many times as you want. The system will only store your best score, so you get a new randomized set of questions each time, and it's a great way to kind of practice different things and also bank, hopefully, some, some marks for as you're collecting marks throughout the course in the various different assessment items. We also have the lab starting up this week, so make sure you do the safety induction before you go. Make sure you wear covered footwear rather than thongs. It's not so much of a problem at this time of year, I guess. So have a go at that as well before coming along. The assignment, the safety quiz rather, and there is a pre-lab quiz which you should ideally do before you go along as well. Right, so like I say, we're going to be moving on now to talk about cosmology. Cosmology is the study of the universe as a whole. So we're going to be talking about how we think, at least as far as our current understanding goes, how we think the universe began and what the conditions were like in the early universe, and then, what the universe looks like today and what we think it might look like, or how we think it might end up evolving as time goes on. So today we're going to be looking at lots of pretty pictures. We're going to be talking a little bit about some of the ways that we observe the universe. The main things that we're going to be kind of needing to take away, we don't need to remember too much of the detail about the pretty pictures or the telescopes or whatever. The main things we're going to be needing to take away from today are sort of how we figure out how far away things are from us in the universe and how fast they're moving. So we'll get to that in a little bit, but we're going to start out with some pretty pictures and stuff. So this is a map of the light that we detect from the very early universe, and we see that it has this kind of fluctuating pattern. So we think that these are seeds of kind of small inhomogeneities in the early universe, and gradually the regions that were very slightly denser in the early universe are where the first stars formed. Now gradually those stars kind of collected together into galaxies, and those galaxies are also not distributed in a kind of uniform way throughout the universe. They're kind of collected together in different structures. And so what we're observing now with our telescopes are the kind of remnants and the imprint of that structure that we saw in the early universe. So then that's what cosmology is then basically the study of the properties of the universe as a whole. And because of the finite speed of light, we can look kind of back in time by looking at stuff that's very far away, because the light from things that are extremely far away has taken a very long time to get to us, and so was emitted much earlier in the universe's evolution. Right, so those are exactly the lights I wanted to turn off. How do I get those ones off that are shining on the screen? Anyway, so what we're looking at here is the Hubble Ultra Deep Field, and we'll get now even more impressive images. The first few are just coming out from the successor to Hubble, the James Webb Space Telescope. This is the Hubble Deep Field. This was, Hubble has looked in lots of directions and seen, it's a telescope, it's looked in lots of directions and seen lots of kind of spectacular things out there in the universe. The deep field was where it basically sat and stared at a very small portion of the sky. And you've got to do that for a very long time. The things that are far away, they're very faint. And so to detect them, you have to look at them you have to look in one direction for a very long time, which is sort of like an expensive thing to do because you're using the telescope for a long time. Anyway, what this is, let's see, the field of view is 2.4 arc minutes. Well, we'll say what an arc minute is in just a second, but basically, this is a region of the sky that's about 1/10 of the diameter of the full moon, so it's a pretty tiny piece of the sky, and it's got a lot of stuff in it, right? I mean, there's most of these things that you're seeing there are not individual stars. These are mostly galaxies that we're seeing, and you can see that, well, one thing that we notice is that they seem to be all different colors, and I guess we'll talk in a few slides' time about the different colors and what that might mean. But this is, I guess, to show that, yeah, there's just lots of galaxies, right? There's lots and lots. And even looking at a very small piece of the sky, then we just see lots of stuff in it. Now, a first Kahoot question for a bit of fun. Bit presumptuous, whoever winner is. Might be true. All right, we're just about ready. How many stars are estimated to exist in the known universe, so the part of the universe that we can observe? More than 10 to the power of 10, that's a 1 with 10 zeros after it. More than 10 to the 14, more than 10 to the 19, or more than 10 to the 24. All right. If in doubt, just go for a really big number. Like when it comes to thinking about the universe, it's just big numbers. So this is something that we do not know the answer to because we can't see all of the stars, but we can make a pretty good estimate of the number of stars that are in the galaxies that are close to us. And then we can use that to estimate how many stars are in the galaxies that we can see that are further away, where there's no way to distinguish the individual stars, but we can look at the galaxy's properties and get an estimate. So there's this kind of nice statement that it's estimated that the number of stars in the known universe is larger than the number of grains of sand on all the beaches in the world, which is kind of ridiculous when you think about it, right? Imagine going and picking up a single handful of sand down on Nobby's beach and trying to count the number of grains. That would take a while. Now imagine trying to do it for every beach in the entire world. So big numbers. Right, we'll see who was quickest on the draw. Okay, come back to that as we go through. So how do we make these observations? I mean, ultimately, the only information that we have about the universe comes from observing the electromagnetic spectrum, comes from observing radiation. So one part of the electromagnetic spectrum is visible light, but longer and shorter wavelengths are also things like microwaves and radio waves. These are all parts of the electromagnetic spectrum, through to X-rays and gamma rays. And there are a selection of telescopes then, some of which are on the ground and others of which are up above the Earth's atmosphere, because there's only certain parts of the electromagnetic spectrum that can actually penetrate through the Earth's atmosphere down to the ground. So if we want to look in certain wavelengths, we've got to go above the atmosphere. Other times we can look from the ground. And looking at these different wavelengths then gives us views of the various kinds of different objects that are out there. So the kind of scale and cost of these telescopes that we have to use means that they tend to be associated with kind of one of the major space agencies in the world. So NASA is the one that more people would have on their t-shirt than probably any of the others. That's the one that you tend to have heard of. NASA has had lots of different observatories that are looking at objects out there in the universe. So one of them that's out there is Chandra. Chandra is particularly focused on X-ray wavelength. There's also the Hubble Space Telescope, which is probably the most famous one. So that was launched in 1990. It's led to a whole bunch of different observations and discoveries, from things like black holes and supernovae to moons and planets and comets, and has also given us more data to pin down the age of the universe, which we will talk about as we go through this week. Now, the really exciting thing at the moment is the launch of the James Webb Space Telescope. So that went through numerous delays and was finally launched at the end of last year. And we just have the first images just now. This is the successor to Hubble, and is going to kind of give us unprecedented new resolution and views and the ability to look back at the very early universe. So it's not just NASA, though. There's also the European Space Agency, which has launched a bunch of these missions. For example, the Herschel mission, which is looking at, again, now it depends, you choose a kind of part of the electromagnetic spectrum, and different parts can tell you different things. But you have to kind of design your telescope in such a way that it's kind of tuned to one of these particular wavelengths. So Herschel is particularly looking at far infrared part of the spectrum, and that allows us to see things that are cool and dusty, as opposed to like the X-ray missions, which show us the things that are really, really hot. And so, for example, that allows us to compare with what we see, how we see a particular galaxy, in this case Andromeda, in visible light compared to what it looks like in microwaves. And then you can start to figure out, well, where are certain things happening? For example, this is showing us the cool dusty material, showing us that there's not a whole lot of that cool dusty material in the region where everything is very bright in the center, where the youngest stars are being born. Right, so it's not only NASA and ESA, there's also JAXA, the Japanese Space Agency, and so on. And there are lots of missions out there that are pointing at different things, but there's so much to look at that there's still plenty that is waiting to be discovered. Right, so we probably know that our own galaxy is called the Milky Way. The Milky Way you can observe, probably not from Newcastle. You've got to go but there are certainly parts of Australia, if you get out in the outback, where you get some excellent seeing, some excellent visibility, low levels of light pollution. And our sun, then, is a typical star that is kind of located some way out one of the spiral arms of our galaxy. Now, the image on the left there is, of course, not a picture. We don't have any way to get an image of our galaxy except from inside it. We've never been able to send cameras. I mean, we've got one mission, what is it, Voyager, that recently we think exited our solar system, but it's still on galactic scales, essentially right next to us. So really that's our only idea of what the galaxy looks like from outside, comes from kind of guesswork. But we think that the Milky Way looks something like this from looking at it from within and looking what other galaxies nearby look like. It's a spiral type of shape. If you look at it edge on, it's basically quite a thin disk with a little bit of a scattering of stars around it, with this kind of central bulge in the middle around what's assumed to be a supermassive black hole at the center. And again, you maybe saw in the science pages on popular media the first images recently, which are thought to be from the radiation around the black hole at the center of our galaxy. So we think that our sun contains something like 10 to the power of 11 stars. Sorry, our galaxy contains something like 10 to the power of 11 stars. Its diameter is something like 100,000 light years. So a light year is a measure of distance. It's the distance that it takes light. It's the distance that light travels in 1 year. But its thickness is only 2,000 light years, so it's pretty kind of thin disk. And the whole thing is rotating. Everything in all systems tend to rotate about one another in astrophysics, essentially because they're of gravitational attraction and conservation of angular momentum. So this disk is rotating slowly, and it'll take something like 200 million years to rotate all the way around once. Right, so here's a question then. How do we know the distance to stars? It's kind of like, most like stars appear as just like a point of light. So how can we tell how far away from us the stars are? Not really obvious how you would do that. Some of the methods are pretty complicated, and we're not going to go into the complicated ones, but here's a kind of somewhat simple example in that you can understand it just with geometry, but it does only work for stars that are quite close to us. So this is called parallax. If we look at the image on the right, the idea is that we make an observation of a star, and we have to make a very precise observation of the direction that we look in to see that star. If we then wait 6 months, the Earth has moved slightly, right, because it's orbited around the sun, and then we can make another observation of that star, and it should appear to us that it's slightly moved, that we have to look in a very slightly different direction to see it. And if we can figure out the change in the angle that we have to look at to see the star, then we can start to draw triangles like we've got here, and we can use Pythagoras' theorem. Yes, did you have a question? Sorry? Why do you assume the star doesn't move? I mean, yeah, I guess to a first approximation, we're assuming, we're using this for stars that are in our galaxy, and we're assuming that the whole of our galaxy is kind of, everything's like rotating rigidly, so they're not moving with respect to one another. Now, of course, that's not, there are going to be like motions of the star that are going to affect that slightly, but to the kind of, I guess the relative motions of the stars are going to be happening on timescales that are longer than 6 months. If you think about the fact that the galaxy rotates over a period of 100 million years, so there are going to be relative motions in there, but they're going to be, I guess, slow enough that we can discount them. Right. So if we've got these, we can do some Pythagoras if we've got these observations, and we can try and figure out from that the capital D, right? That's the thing we want to know. It's the distance from the sun to this nearby star. We know, at least approximately, again, there are approximations. The Earth's orbit around the sun is not a perfect circle, but we have a sort of average for that, for the diameter, or the radius, rather, of the Earth's orbit. Right, so then it turns out, obviously, this is not to scale, right? This shows the nearest star as being about the same distance away from the sun as what the Earth is, which is clearly not to scale. In reality, these triangles are enormous. I don't know how many hundreds of meters above the lecture theatre the nearby star should actually be if this were to scale, but it would be an extremely elongated triangle. And so the angles that we're talking about are tiny, and they're measured in something that's called arc seconds. So if you take a degree, so 360 degrees in a circle, if you take 1 degree and you split it up into 60 segments, those are called arc minutes. And then if you split each of those into 60, those are called arc seconds. So 1 arc second is 1/3600th of a degree. So usually we're measuring in arc seconds in these tiny increments of angle. Right, so we're going to try and do an example here. If I can switch over to the document camera. Okay. So we're going to try and estimate if we've got a given star and the angle theta in this picture is estimated to be 89.99994 degrees, then we're going to try and figure out what the distance is to the star. So I guess the first thing I'm going to do is to calculate phi. So phi would just be 90 minus theta, right? Since the angles of a triangle add up to 180, and we've got a right angle in there. So that means that phi is 0. And then we've got to get the right number of zeros, 0.00006 degrees. So now we've got this right angle triangle with phi and capital D, the thing that we're trying to find, on one side, and lowercase d, which we know 1.5 times 10 to the 8 kilometers is roughly the radius of the Earth's orbit. So now we could use tan phi is, what's tan phi? It's opposite over adjacent, so it's little d over big D, right? So this allows us to rearrange and write big D as little d divided by tan phi, which is 1.5 times 10 to the 8 kilometers divided by tan of 0.00006. And now, so long as you've got your calculator set to degrees instead of radians, you should be able to plug that in calculate that tan, and then get the distance to the star as approximately 1.4 times 10 to the 14 kilometers. So quite far away, but this would be not actually in cosmological terms. This is right next door. This is very close to us. Seem to have another Kahoot question. How many kilometers in a light year? Any idea how fast light travels? Ah, excellent. Okay. Right, so we said that the closest stars to us are within a few light years. And, well, we came out with 10 to the 14 for that last example. So the closest stars are around about a few light years away, and a light year is around about 10 to the 13 kilometers. Winner and winner 2 are looking good. Right. Right, so here's an artist's impression of the Milky Way and our sun, roughly indicated, although I think the arrow once moved a bit because it seems to be pointing in between the spiral arms, which is a bit dubious. Should probably be moved a couple of centimeters lower down. So our galaxy, we think, is something like 100,000 light years across. There are also kind of smaller collections of stars located close by. These are called globular clusters. They're not quite big enough to be considered galaxies, and those might only contain on the order of 1 million stars, just 1 million. So we've got these globular clusters that are nearby, but there are also, if we look slightly further afield, there are other galaxies as well. And galaxies tend to be collected. Again, they're not kind of distributed evenly in space. They tend to be collected together in little groups, in clusters. So the local group of our galaxies is a member of the Virgo supercluster of galaxies. And so these Magellanic clouds, small and large, kind of nearby to us. One of the closest other galaxies is Andromeda. Because of gravity, everything is kind of being attracted together, so we're moving towards the Andromeda galaxy at what seems like a slightly frightening breakneck pace of 3 times 10 to the 5 kilometers an hour. And we think that this is due to not just the mass of the two galaxies attracting, but some large invisible mass in between the two galaxies, which is kind of pulling us both towards it, and we'll talk about this kind of invisible mass a little bit as we go through this week. And not only are we being kind of pulled together with our local group of galaxies, but our local group of galaxies is also being pulled into the center of the Virgo supercluster at something like 2 million kilometers an hour. So it's a good job. Anyway, it would be kind of slightly disruptive if we were still around when the galaxies collided. Fortunately, the distances are so large that it's still going to take a very long time for any of these any of these things to happen. So this is kind of going back now a little bit to these ideas in that initial video where this arrangement of galaxies was seeded by the conditions in the early universe. So very shortly after the Big Bang, we think that the density of material was not completely uniform everywhere. There were some regions where the density was slightly higher, and gravity will cause cause the matter to be attracted into those denser regions, and so that will gradually be amplified. And it's within then those dense regions that the first stars form, and then the galaxies and the clusters of galaxies, and indeed the superclusters, will all grow out of those sort of early regions where things were just slightly denser. So like I say then, the galaxies tend to be collected into these clusters. A cluster of galaxies might contain on the order of 1,000 galaxies. And then those clusters are again not just randomly distributed in space, but they tend to form kind of close to one another and in certain structures. Turns out that they tend to be in filaments, which would be a kind of one-dimensional structure in 3D space, kind of like a line, or in walls or sheets, which would be sort of like a two-dimensional distribution in 3D space. And this is something that we don't really quite fully understand, why they form into these kind of shapes rather than blobs. And, there is lots of active research on, lots of the areas that we're talking about here. But we think that this is all, like I say, seeded by the types of distributions that existed in the early universe, which then are what these galaxies kind of grew off of, if you like. Right, so another question. How far away are the closest stars to the sun in kilometers? 10 to the 9, 10 to the 13, 10 to the 16, or 10 to the 19? Ten to the 13, yes. So the closest stars are around about a light year away. Right, now it turns out that although I talked about the fact that we are moving towards some of the galaxies that are closest to us, if we look in general at all of the galaxies that we can see, most of them, almost all of them, are moving away from us. And not only that, they're moving away from one another as well. And this is kind of one of the clues and one of the ideas that leads us to, that feeds into this Big Bang theory of the evolution of the universe, that it appears that all galaxies are moving away from one another. So presumably at some earlier time they were all much closer. Now not only are all galaxies moving away from us, but the speed that they're moving away is dependent on how far away they are. And the furthest galaxies are actually moving away from us faster than the galaxies that are close by. Now, we said that we had this kind of parallax method for determining the distance, but that doesn't really work for galaxies. There are much more kind of subtle things that we have to do that we're not going to look into here for how we determine the distance. How we calculate the speed that galaxies are moving away is a little bit more straightforward. The Doppler shift is probably something that you're familiar with, the idea that, you know, the pitch of the ambulance or the fire engine siren as it approaches you and then moves away changes. This is the Doppler effect, the fact that the wavelength of the wavelength of the sound in that case is kind of compressed or stretched depending on whether the object is moving towards or away. We'll talk about that in more detail all the way at the very end of the course when we do waves and oscillations in the last 2 weeks. So the same effect happens with light. So we know that light is a wave. We can think of it as both a wave and a particle, which gets a bit, well, then you've got to wrap your head around all that stuff. But one way to think about light is as a wave. And again, we get the same effect happen with the waves of light as we do with the sound waves from that fire engine. Now, if the object is moving towards us, then the wavelengths are shorter, and that corresponds to shifting towards the red end of the spectrum. Sorry, I just said that completely the wrong way around. If it's moving towards us, it's compressed, the wavelengths are shorter, and it's moving towards the blue end of the spectrum. On the other hand, if the object is moving away from us, then the wavelength is stretched out, and that corresponds to shifting towards the red end of the visible light spectrum, and so hence this is called red shift. Now, the way that we calculate how much the wavelength of light changes is using this formula here. And this is the standard Doppler shift formula. So lambda naught is the wavelength that the light is emitted at. Lambda is the wavelength we see, and c is the speed of light, and v is the object, the speed of the object. So if we know lambda and lambda naught, and we do know the speed of light, then we can calculate v, the velocity of motion of that galaxy. Now, a couple of notes. A couple of important notes. The first one is, and this you can, so long as the speed is not too close to the speed of light, you can rewrite that equation approximately in the form that's here under note 1, and that tends to be, well, it's a little bit simpler to calculate if you use that formula. I think that's the one we include on the tutorial sheet. The other note is that, strictly speaking, the redshift that we see, although I've just gone through and explained everything to you in terms of Doppler shift, strictly speaking, the redshift that's observed is not from the Doppler effect. It's the wavelength of light is not stretched due to the speed that the object is moving away necessarily, but it's sort of indirectly that. It's actually stretched due to the expansion of space-time. So then why on earth do we use the Doppler effect formula? Well, it turns out that so long as v over c is small, the effect of that expanding space-time doesn't give much of a change to this formula. So long as v over c is small, again, we can use this formula. We just are going to be aware that it's not, strictly speaking, just the Doppler effect and the motion. The main part of that redshift is actually coming from the expansion of space, so that the whole of space is getting stretched, which stretches those wavelengths, stretches the wavelength of the light again. Right, so we're going to do a little example. Typically, again, all we observe from out there in the universe is the electromagnetic spectrum. That electromagnetic spectrum has, we've got all the colors, and then we've got, all the different kinds of radiation, but it's not a completely smooth function. There are little peaks and troughs in there that are signatures of, like, the elements that are in whatever it is that we're looking at. And one of the kind of classic examples that is used is that sodium produces a so-called doublet, a pair of peaks or troughs, depending on whether you're looking at emission or absorption. And so if we look at that and we observe it at a slightly different, if we look at that pair of peaks or troughs and we observe them at a slightly different location compared to what they should look, what we know that they are in the laboratory, then that allows us to estimate the speed using that change in wavelength. Now, you're going to have a go at doing this in the lab next week, I think, for a bunch of examples. So we're just going to try and do a calculation here. And we've got information about what the wavelengths of those two lines are on Earth, so what they would be if the speed was 0, and those are 589.6 and 589.0. And we're told that for a given galaxy, when we look at the spectrum from that galaxy, we see these sodium lines, but they appear instead at 593.0 and 592.4. So that difference in wavelength, we're going to try and convert into a speed. Now we can use either pair of wavelength measurements. It doesn't matter. We're going to use those two there. But we could also use the second part of the doublet as well. We'd get the same answer because it's the change in wavelength is the same. So we've got lambda, that's the observed wavelength, is 593.0 nanometers. And we've got lambda naught, which is the wavelength that we know that sodium emits at. That's 589.6. So then we're going to substitute into this formula. And I'm going to use the more complicated formula here, but you can check it, if you like, with the simpler formula that we're going to use in the tutorials, and you'll find that you get a very similar answer. So that should be lambda over lambda naught squared, that 1 plus v over c, 1 minus v over c. So that's 593.0 divided by 589.6 squared. A bit of calculator work again gives us that as 1.0116. And so now we've got to rearrange this. So we want to multiply both sides of our equation by 1 minus v over c. So that gives us 1 plus v over c is 1.0116 times 1 minus v over c. And now we want to rearrange our equation and put all the terms in v over c over on one side. That'll give us 2.0116 times v over c is equal to 0.0116. And so v then is 0.0116 divided by 2.0116 times the speed of light, which would be 3 times 10 to the 8 meters per second. And the answer, if we convert to kilometers per second, should be 1730 kilometers per second. Right, so like I say, there will be lots of practice, lots more on doing this in the lab. But this is principally how we determine how far away all the galaxies, how fast all the different galaxies are moving away from us, is by this redshift. So then to figure out the age of the universe, I already mentioned this before, we tend to look at galaxies that are at different distances away from us, and the light from those distant galaxies takes longer to get to us, and so therefore we're looking back in time. Now, why is the Hubble Space Telescope called the Hubble Space Telescope? Well, it's named after Edwin Hubble. He was the first to discover that the redshift, and therefore the speed at which the galaxy is moving away from us, is proportional to the distance. And if you plot this, you don't get a perfect straight line like we've got here. If you put lots of galaxies on us, you get a lot more kind of scatter around that. But this distance of recession, then the speed that it moves away is proportional, linearly proportional to the distance. And this V equals h times r. H is called Hubble's constant. It's just the gradient of the best fit to that line. And our best estimate for what Hubble's constant is at the moment, based on the data collected, is given by these numbers here, 67.3 kilometers per second per megaparsec. Right, so this then gives us a way to estimate how old the universe is. So we already had this Big Bang hypothesis before Hubble made his measurements, but now that we have this idea that everything is moving away from each other, and we've got an idea of how fast it's moving relative to how far apart it is, that allows us to estimate the point in time at which all of these galaxies were in the same location. So we'd like to estimate the time that it's taken for these objects to get the distances apart that they are at the speeds that they're traveling. It's all a bit of an estimate. We're making lots of assumptions that they were, uniformly moving and all sorts of things. But based on all of that, a first approximation would just be to say that the time is just the distance that they've traveled divided by their speed. But now, based on Hubble's law, we can replace the speed by Hubble's constant times the distance, which then allows us to cancel out the two factors of the distance, and we just get that the age of the universe is 1 over Hubble's constant. Now, one set of units for Hubble's constant would be 20, what do we have over here? We've got 20 kilometers per second per mega light year. And now we want to convert that into some kind of sensible units. The 20 on the bottom here, this comes from the fact that this is 1 mega light year is 1 million light years, and 1 light year is 10 to the 13 kilometers, and so we have to multiply. This is the conversion from a mega light year down into kilometers. The factors of kilometers will cancel out, and we'll eventually get a number in seconds for the age of the universe. 5 times 10 to the 17 seconds. And it's a bit of a weird thing to try and do that in seconds, so then we want to convert from seconds to years by dividing by 60, and then 60 again, and 24, and 365. And we'll end up with the age of the universe being estimated as something like 15 billion years. So there are lots of assumptions that go into this, and there are certainly ways to argue that there's a lot of uncertainty there. But there are various other estimates that we can make from other measurements, and those seem to be roughly consistent. And so this is giving us some kind of confidence that this is a reasonable estimate. Now, I'm going to skip this last bit here just because we're running out of time. And we'll cover that next time, and we'll just have one last Kahoot question to finish off. What causes the very large redshifts of extremely distant galaxies? Is it the Doppler effect? Is it the stretching of light waves as they traverse an expanding universe? Is it differences between stars that existed in the past and those that exist today? Or is it a gravitational force on photons as they leave distant galaxies? Yes, it is the stretching of light waves as they traverse the expanding universe. So we'll talk about this expanding universe much more next time, but what everybody wants to know is who's on the podium. James Webb, nice. Oh well, winner and winner two. Yeah, winner two. Right, okay. Well done to our podium scissors. Right, so we'll pick it up there and we'll talk some more about the universe on Wednesday morning. So remember, labs and tutorials start this week, and I'll see some of you guys in the tutorials this afternoon. Hi.
If I didn't do like physics in school and I did an open foundation, should I be taking like an easier course or speak
I mean, I think you should probably be all right. Do you have the choice, depending on your program, you might have the choice to do like this one or 1205,
Yeah,
is that right?
I can do 1205.
Yeah.
It doesn't go towards our course, but it just gets the credit anyway.
Yeah. I mean, the difference between the two is, like, they'll cover a lot of the same topics, but yeah, things are done, I guess, a little bit more slowly. There's a little bit less material and a little bit less maths in 1205. So maybe it's more down to, you know, if you're kind of confident enough on the math side, it probably shouldn't make that much difference which one you do. That's kind of the main difference with the 1205.
Just a math level.
Yeah, mostly. So it was put in for, you know, there's a bit of calculus in this basically, and 1205 is like the attempt to strip all the calculus out. So. Yeah. All right. No worries.
There's another question. I can't find SD building on map.
Okay. So because the next class is going to start, can I help you just outside here? Just now, because the next class is going to start. So I'll show you. I'll just see. Yeah, I'll come outside the door and. Yes, just now. Just let me log out and make some space for the next people. No, that's all right. But you need to. It's nothing worse than struggling to get set up and the recording started already, and you know.